Hi, my name is Daniel Selva, and I'm an assistant professor at Cornell University in the Systems Engineering program and in the Mechanical and Aerospace Engineering department. I'm also a director of the Systems Engineering, Architecture, and Knowledge Lab that we call the SEAK Lab. My research is fundamentally about systems architecture, which is about designing complex systems. For example, let's imagine that you wanted to design the next generation of weather forecasting satellites for NASA or NOAA. You would need to take different measurements of several atmospheric parameters, things like atmospheric temperature, humidity, pressure, and things like that. In order to do that, you're going to need to have a wide range of remote sensing instruments, things like radiometers, sounders that are going to use different frequency bands in the spectrum. You're going to need to put those instruments into different spacecraft buses that have batteries, solar panels, antennas to communicate with the ground, and things like that. So all in all, it's going to be a complex system because it's going to have a lot of components, a lot of interactions between the components, and it's probably going to cost several hundreds of millions of dollars and several years to develop. The way I think about systems architecture is as a decision-making activity. So architecting a system is all about making design decisions. In particular, we try to think about what are the top 10 design decisions that you would have to make in a system, because those are likely to be the ones that are going to drive most of the performance, the cost of the system, the risk, and other metrics of interest. Often in systems architecture, we like to reason in abstract terms. So for instance, if we have to decide whether we want to put all of the instruments in a single spacecraft or distribute them across multiple spacecraft, instead of thinking about that specific problem, we're going to try to generalize that and think about the general trade-off between what we call monolithic architectures, where you put essentially all of the eggs in the same basket, versus distributed architectures, where you distribute the different eggs across multiple baskets. So following this idea, we took different systems architecture problems across multiple disciplines and tried to get rid of all of the details and all of the domain-specific things and look at the underlying mathematical structure of those decision problems. And what we found is that there are actually 6 decision patterns that appear over and over in systems architecture. So for example, the eggs in a basket problem, we call that the partitioning patterns. And there are 5 other of those patterns that are essentially different graph problems. One of the things that makes systems architecture really challenging is the complexity of those decision problems. Now, if you have a million different architectures with a lot of combinatorial design decisions and more than one metric, this becomes really challenging. How do you even do that? So one of my grad students has actually developed a new technique, visualization technique, that he calls city plot. And it does exactly that. The way it works is that it uses a technique from machine learning called dimensionality reduction that condenses all of the information from the design space into 2 dimensions. And then we use the 3rd dimension to essentially condense all of the objective space information. So for example, each of the points on this scatter plot represents one architecture, and the distances between these points represent how different these architectures are. And then on each point, we're going to plot 1 bar for each of the metrics, and the height of those bars is going to be proportional to the value of the metrics. So what this creates is essentially the idea of design landscape, which is what we wanted in the first place. The vision I have for systems architecture is one in which intelligent design agents collaborate hand in hand with humans, just like humans and robots may collaborate in the future for manufacturing. An example where that could be useful is in what we call the knowledge discovery problem, which is essentially the problem of finding what good architectures have in common. Humans are great for that because they have common sense and they may have a lot of domain-specific knowledge that they can use for that. But on the other hand, they're limited in terms of their computational power. Machine learning algorithms are great because they can find complex statistical relationships in large data sets. But for this particular problem, they don't quite work because the number of features that you have to explore is too large. So what we do is that we engage in a dialogue between the humans and the computers, so that the human proposes high-level classes of features for the algorithms to explore, and then the machine learning layer will determine which ones of those are actually dominant features. System architecture is an exciting field of study that brings together design, analysis, optimization, machine learning, data visualization, knowledge representation, and human psychology in order to tackle the amazingly complex technological opportunities of the modern world.